Hi, my name is Liupei. I would like to present our work on self-supervised learning for facial action unit recognition through temporal consistency. First, let's start with the overview of the paper. Facial expression has inherent temporal dependencies which can be leveraged in the automatic expression analysis. In this paper, we propose a self-supervised representation learning methods for facial action unit recognition by utilizing the temporal consistency. So we use a triplet-based ranking approach, which will train the encoder that can rank the frames based on their temporal distance from the anchor frame in embedding space. Then we show that our encoder actually learns meaningful representations for AU recognition without any labels. And the encoder is evaluated for the AU detection tasks on various datasets, including BP4D, EmotionNet, and DSFA. Our results are comparable and superior to state-of-the-art through the self-supervised learning. So let's talk more about the background and motivation. Basically, facial action unit detection requires a large amount of manually labeled data, which may be expensive or difficult to obtain. However, there exists huge amount of unlabeled data from videos, and we can actually get from online sources. There are two mainly common approaches to learn from the unlabeled data. The first one is called self-supervised learning. Basically, the self-supervised learning requires no manual labeling of the images. Instead, it directly learns the representation through the proxy loss. Then we can further apply the learned representation in various downstream tasks. So another one is called unsupervised domain adaptation, which is achieving by learning a task in source domain and trying to map into target domain through domain invariant training. In that way, it can adapt for a variety of people and apparatus. The key idea for the paper is to utilize the inherent temporal consistency lies within the facial expression. For instance, given the sequence of frames from video, we randomly select an anchor frame at t0. Then we calculate the L2 distance between the anchor frame and the positive frame at t equal to n in embedding space. We also calculate the distance between the anchor frame and the adjacent frame at t equal to n plus as negative frame. In the end, we use a triplet loss to make sure that the positive distance is always more than the negative distance in order to maintain a correct temporal order. Then let's talk about our detailed methods. We propose a parallel encoder network which takes a sequence of frames extracted from videos as an input, as shown here. The anchor frame is selected as time t, and the sibling frame is selected at t plus 1, and the following frames are selected at an equal interval from t plus 1 plus k to t plus 1 plus nk, where those k stands for the constant interval. And all of those inputs are fed into the ResNet 18 encoders with shared weights, followed by a fully connected layers to generate 256 dimension embeddings. We then compute the triplet losses for adjacent frames, pairs along with a fixed anchor frame. In each adjacent pairs, the preceding frame is treated as a positive frame, and the following frame is treated as a negative sample. Finally, all the triplet losses are added together to form the ranking triplet loss. Let's talk more on the temporal ranking triplet loss. Basically, we compute the sum of each individual triplet losses between the adjacent frames in sequence. So given a set of sequence embedding and the L2 distance function d as the input, and we having the every nth triplet involves consecutive frame pairs from the sequence, where xn minus 1 is a positive sample and the following frame xn is a negative sample. Finally, we take the sum of the all triplet hinge losses to ranking the entire sequence in the correct temporal order. Then I would like to show some evaluation results. Basically, our network is trained on Vox Level 2, which involves people talking videos. And we evaluate our learned embedding on public datasets for facial action unit recognition and facial expression classification. For example, the BP4D, the DSFA, EmotionNet, and AffectNet. For BP4D and DSFA, those are measured by the F1 score, whereas EmotionNet and AffectNet are measured on AUC, which stands for area under the ROC curve. As you can see, our performance we have superior performance on all of the 4 datasets compared to the state-of-the-art self-supervised learning, the FabNet and the TCAE. Then I would like to show some qualitative results. To help us better understand the learned representation, we perform an image retrieval task on EmotionNet to demonstrate the ability of the representation to capture expression similarities. Basically, the similarity is measured by the cosine similarity relative to the query examples. In order to cover diversity of the facial expression, we have select different kinds of expressions such as green, surprise, and contempt. For instance, the query on the third row shows a man wearing glasses with closed lips, and our retrieved images consist of similar facial expressions regardless of the glasses or not, which shows our learned embeddings are independent from the facial declarations, which further demonstrates the generalizability of our learned embedding. To conclude, we have proposed a simple yet powerful self-supervised methods for facial action detection, and we have achieved state-of-the-art performance comparing to other methods. And also the qualitative results demonstrate the learned representation are relative and generalizable for facial expression and head pose. And you can also find our implementation code and train model weights on the following links on GitHub. Thank you for my presentation.